Okay. Working?
Hello, hello.
It is okay? Okay?
Yes.
No? Okay, thank you for the organizers. Thank you for the introduction. And I really appreciate the opportunity to be here and to talk about my work. Today, the title of my talk, it is Beyond Topological Hyperbolicity. And it's not coincidence that the first time that I was in Poland, it was to the conference called Beyond Uniform Hyperbolicity. I am here. And it was also the first time that I meet Felix. You can see that Felix is here. And my history with Felix was really similar with the Christoph history. I just make a really stupid question, and he just I thought I was smart, and I thought it was a good question. He just said something like it's trivial and show me really after yes, we met in Brazil after this. And this one was 13, right? And we met in 14 or 15. Okay. Okay. Now it's okay. And it is for sure, Felix is the responsible that I am working in Poland for more than 3 years. And so I would like to say thank you, Felix, and happy birthday. Come back to the talk. We have these, in this conference, it is Beyond Uniform Hyperbolicity. I would like to start talking with a quote from Lawrence that he said that a butterfly flapping its wings in Brazil can produce a tornado in Texas. This is you have to remember this is Brazil. Sometimes you see this quote with another country, and it's not true. It's the original, it's Brazil. Okay, and also this was the nice way to try to explain for non-mathematicians what is sensitivity to initial conditions means. And it's really easy. It's just if you have one point in the system and a neighborhood, any neighborhood of this point, you can find another point in this neighborhood that the iterated of these 2 points, they not are close for every iterated. They was to separate it in some point in the future. And then we can just claim that the uniform hyperbolic systems they are inside of the sensitivity to initial condition systems. This is a smaller set. It's smaller set if you want to think about this. And how we see this, it's just easy application of the shadowing lemma, and the really popular and basic shadowing lemma that say that shadowing lemma is a curious creature that exists in only 2 dimensions and eat mathematicians. This is what is in this book of The Color of May or Magic. There is this shadowing lemma there, and I just want you should know this because shadowing lemma is scary, they can eat you. But the real shadowing lemma just established that uniform hyperbolicity implies expansivity and shadowing, and expansivity and shadowing is exactly what the definition of topological hyperbolicity. So what we have here is we have uniform hyperbolicity, and we have topological hyperbolicity a little bit bigger. So here we are already beyond uniform hyperbolicity. And my approach is try to, of course, there are many ways to go beyond uniform hyperbolicity, but here, for me, I am interested to go beyond uniform hyperbolicity from the topological point of view. And in this talk, I am going to show some other, to try to make this set bigger in some way. Indeed, I will try to show some, like three other sets. Of course, we have to explain why it's worth to study these sets and what this set means for us. Okay. So okay, now let's go to the setting, be more talk more about math. Our setting, it's basically we'll always talk about in a homeomorphism defined in a compact matter space. This flows here. I think I shouldn't have put this here. I just forgot to delete. But in this project, we have works in flows, in just continuous and surrogate maps, in set-valued maps, and also in iterated function systems. But here today, I'm just talking about homeomorphisms. So now let's go to the definitions. This is the definition of stable and unstable sets. They start with the local stable set and the local unstable set. They are the local unstable is just the local unstable to the past, and the local stable is just the set of the points that are of X is the set of the points Y that are always epsilon close to X. And also we have this another set here that is the stable and unstable set that is, instead of just stayed epsilon close, they go to zero. The iterated of them asymptotically go to zero. But notice that these two sets can be totally different because I would like to draw here, but the difference, but it's really simple to see an example of Y that is in the local stable set, but it's not in the stable set. And also it's easy to find the one that's in the stable set, but not in the local. Let's go to the next one. C is the definition of sensitivity to the dependence of initial conditions that I just talked before. This is the precise definition of expansivity. Here I just put N in Z, but indeed, in general, we just talk to the future, just N in the natural numbers. I just put Z here because it's easier to see that expansivity implies directly this sensitivity here. But if you have a little bit more that just a compact matter space, you have some locally connected or something like this. So the unstable set of X, it's always no-empty. The local unstable set is always no-empty. So this point that's there, that's not X, they have to separate, be a part of the iterator of X in the future, not in the past, because they are in the stable local, they must be always closed. So just to remember that this ball is called the Bowen ball. This set here. And here is the traditional definition of shadowing property that for each epsilon, there is delta tau such that if xi is a delta pseudo-orbit, then you will have a shadow for this delta pseudo-orbit. This shadowing, it's really interesting to the application, because you always, when you are in a computer, you don't have the real data. What you have, you have some errors, but in general, what you so what you think you are looking, it's an orbit, is not. It's just a pseudo orbit. So these properties show that when you have this property, it shows that when you have a pseudo orbit, if it is a good pseudo orbit, so you have an actual orbit that follows one. So this maybe don't take care of this, maybe explain why sometimes the simulation don't work, because they don't take care of this kind of stuff. And here's the definition of topological hyperbolicity. That is passivity plus shadow. And here is the definition of the formal definition of uniform hyperbolic set, diffeomorphism. But to define this, we need a little bit more structure. We need a manifold. We need a C1 diffeomorphism. And what it means that when you have, when you have the tangent space, it's splitting into different spaces, that one is contracting and the other one uniform contracting indeed, and the another one is expanding, but the correct way of say this is contracting to the past, right? So we have these two inequalities here is exactly this. So here I am going to just show these examples that are really basic, but I will talk about these examples later. I use this example later, so I would like to show that, to make you understand what I'm talking about. I use A and stuff. Here we have this matrix in R2, 2, 1, 1, 1, and then we have this quotient that show in Z2. So we have like this side is related with this side, and this side is related with this side. So we have indeed a torus, and we have this really well-known example, that's the cat map. Here we have also the example of the Smale Horseshoe, that Smale in an interview claimed that it was he had this idea in a beach in Rio de Janeiro. So it's really easy. You just have this square with these two half of disk, and you just use some compositions to make it in the shape of a horseshoe, and then you consider the maximum invariant inside this square, and this maximum invariant will be the horseshoe. And this horseshoe, it's an example of it's conjugated to the shift map. The shift map is just you have two symbols, 0 and 1, and a sequence of with these two symbols. The sequence not just forward, but forward and backwards. And then you have this distance defined here, and here. And the shift map that just take any coordinate and jump for one backward. So these three examples are classical example of this two. This one is an example of uniform hyperbolicity, these two are examples of topological hyperbolicity. This Smale horseshoe you can make like a hyperbolic set in the sense of uniform hyperbolic set. If you glue this in a sphere, there are ways to do it. But okay, so here I am just listing the examples and also put the second iterated of the horseshoe. Now let's go to the oh yeah, I have to talk about this result first. The chain recurrent set. How to define it? We have a point x. It's related with a point y. If for each delta, you can go from x to y by a delta pseudo-warp, finite delta pseudo-warp, and from y to x, you can go with a finite pseudo-warp also. So if you have this property for all delta greater than 0, you have these 2 points. These 2 points are related. And the chain recurrent set is just the set of the points that they have this chain recurrency with itself, that is related with itself. And then this relation, it's an equivalent relation inside of this set. And a chain recurrent class is just the set of x, is just the point y that is related with x, with the standard. And then we have here the spectral decomposition theorem, that when we have f restricted to the chain recurrent set as expansivity and shadowing property, it's just a homeomorphism, okay? You have this set, it's a union of finite, it's a finite union of basic sets. This finite, it's the key here. And basic sets are invariant, compact, and they are transitive. And the second part is not that important because I'm not using too much, but it's each of these ones can be of the basic sets can be decomposed in a finite union of elementary sets, and you can go from one to another to come back to the first one, and they are compact. And when you restrict when it come back to itself, we have these guys restricted, this iterated restricted to CI, it's topologically mixing. Where this iterated is exactly the iterated of number of elementary sets that decay the union. Okay, from now let's go to the. It is just the basics. Okay, now we are going to the new stuff. Okay, this will be our toy model. This will be an example that has shadowing, as a dense set of periodic orbits, is transitive, and has the shadowing property, but it's not expansive. So this guy is it's beyond the topological hyperbolicity. It's not topological hyperbolic because it's not expansive. And this one will be our toy model. How we construct this one? It's really simple. You have the torus that we saw before when we were looking the Anosov homomorphism, and we just relate all the points with the negative and make this quotient. And then what we have here is the sphere. And then this map, the cat map, induce the pseudo Anosov on the sphere. I would like to try to draw this thing. I think people that are online will be not able to see really well, but I would like to explain how we have this shape. Basically, what we have is a square. We have it is 1/2, and then we have when you make this torus, this line is related to this line is related to this line. When we make this another relation here, this relation here, what we have is this square is related with this square, and this square is related with this square. So here is the origin, 0. So okay, it is, well, where is and what we have is this square is related to this square, and this square is related with this square. So here is the stable set of the fixed point. So when we go to the end, we have the unstable set. Since this square is related to this square, this line will be related with this line. So when we see here in this, here, we have the stable set that was two lines become only one, is S1 here. And also, it also happens with the unstable that become only one. And when you look to the other state, the stable foliation, the unstable foliation, what happened is these unstable foliation, it cuts this one once and part 2, and what happens is in the neighborhood of this fixed point, when you are already in the sphere, we have this shape here. So this is what is different, and it's not expansive exactly because this we close really close to the periodic point. We can find of this fixed point, we can find points here that are always close. If iterators are always close. I'll explain better how to prove this later. And now we have the new property. It's called L shadowing. The L shadowing, it's really similar with the shadowing property, but we have a little bit more. That is for every epsilon, there is a delta, such that almost the same thing happens when you have a delta pseudo orbit. But this delta pseudo orbit is not just a delta pseudo orbit; it must have some additional property, that this one, that for asymptotically, they go to the distance, not just stay delta close, they go to 0. So what we have is we find a shadow, like in the shadow, and we also find this shadow has an additional property that here, like a shadow is here, and has the additional property that is not just stay epsilon close to the iterators of the pseudo object, but it's go to 0 asymptotically. So this thing it's already much stronger than just shadow. And indeed, when we have topological hyperbolicity, it implies this L shadow. And when we have expansivity, we have this really nice property that the local stable set it's inside the stable set, and also for the unstable set. This property plus the property of the shadowing property is enough to prove the first part of the spectral decomposition theorem. So in a paper in 2020, I should put here before that is a joint work with Alfonso Ortigui, Bernardo Carvalho, and José Viegas. In this paper, in the journal Differential Equation, we have that are equivalent that F has the L shadowing, or F has the shadowing property plus we have this thing that really looks like what we have for expansivity, but it's not the same. Here we have local. Here we don't have any local. What we have is any point in the Bowen ball of X, which means that this point, the iterator of this point is always delta close to the iterators of X. So they just not just follow that asymptotically the distance go to 0. And with this thing plus the shadowing, we can prove the first part of the spectral decomposition theorem. So for this L shadowing, we have this property. And one example with that have this problem, but it's not topological hyperbolic, is this one, our toy model that I just repeat. But we have another example here. This first example I first saw in a paper of Bernardo and Dominic. I don't know if this example exists before or you created this. Dominic can explain if it already exists. But this example here is a little bit complicated, but it's really easy to understand when you have the picture. So we just take two numbers, natural numbers, P and Q. Here I choose 3 and 4. And then we consider the space of the shift with P plus Q minus 1 symbols. So, and this guy is this X 3, 4, that X, P, Q is just the subset of this shift that with P plus Q minus 1 points, that the only allowed sequence are these two, the sequence that follow this graph. That, or you have to, from 0, you have to come with these to 1 and then to 2 and then come back to 0. It means that you have to walk here P times, or you have to walk here q times. So this is this space X 3, 4 here, but you can do this for P and Q in general. And one nice property that these guys have, it is a subshift of finite type. And the second property that is here, that if you have a periodic, the periodic pointers of these guys are as the periods are at least the equal P. Mean that cannot you don't have periodic point smaller than P, because I am choosing P always the smaller one. For example, here, if you want a periodic point, the periodic point, the smaller periodic point for this X3, 4 is the periodic point that the sequence has 0, 1, 2, and 0 again, and repeat. So it's 3. The period is 3 to come back. So so now let's go forward. We take this this Pn. It's a sequence of prime numbers that go to infinity, and we have this sequence Xn with this property that I just described, and we have the shifts here. And then we consider this map that is the product of all these shift maps here. So nice property of this map is it don't have any periodic point, because if F has a periodic point, you this periodic point should have one coordinate, should be periodic, and for all these coordinates, each coordinate should be periodic for all these guys, and we fit the period of the periodic point of F, but the period points of the sigma n's go to infinity, because Pn, the sequence Pn's go to infinity. This is why we chose prime numbers. So, and one thing that we can prove that this example, it's also has the L shadowing. Yeah, it's topological mixing. It is everyone already know, and has the L shadowing. And the set of periodic points of this map here should be the big F of this small f, capital F, right? So then we have this is the main theorem of this paper, that if you a homomorphism that have the L shadowing property, then it's this homomorphism is tame. Tame means that it has only finite number of chain recurrent sets. That is the first part of the spectral decomposition theorem, and each chain current class is either expansive or contain arbitrarily small topological semi-Horseshoes. And what means this arbitrarily small topological Horseshoes? Means that for any delta, we can find a iterated of the homomorphism, that for this iterated, we can find a semi-Horseshoe that is only a set that's semi-conjugated to a shift. And I am not going to give the proof of this one, but I am going to show this. I have to draw again, but I am going to show how the semi-Horseshoes appears in the in our toy model. Our toy model is basically this way. We have this nice picture here. So so when do we I should be started with the other one. Okay. Let me come back. In the Anosov, we have the following. We have a periodic point, and we have the stable and the stable. So it's really well known that we have here intersection, and when we have this intersection, we have the horseshoe, but the horseshoe here, the Anosov, it's big. The cat map, the horseshoe here is big, but when we go with to for toy model, what we have is if delta is small, we can just find here is the fixed point. We can just find a periodic point really close to this fixed point, and then we have what we have is horseshoe. And this horseshoe can be really small. We do have a sequence of horseshoes going to with the diameter going to 0. Of course, this is not horseshoe for the map. Horseshoe for iterate of the map. Indeed, the iterate of the map is exactly the iterated of the period of this periodic point. So this is our main result, and it's curious that we have this small topological small horseshoes, because when we go to visit the expansivity again, we have this definition of N-expansivity that it's exactly the same definition of expansivity, but instead say that this set here has only one point, only the point X. We are just limiting the number of set of points here. But so assume that n is equal to. So this is really close to expansivity. But this theorem here, this theorem here says that we contains this arbitrarily small topological semi-horseshoes. So, or when we have that property, or we have expansivity, or it cannot be N-expansive for Nn, because this set or this horseshoe must be a contour set, have to contain a contour set. So it is a curious set. So how much time? 7 minutes. Maybe I can talk some words about generalization of expansivity. It's also we have these other definitions here that when n is equal to 1, it's exactly the expansivity, and when n expansivity always implies n plus 1 expansivity. Means we have a sequence of sets. One contain the bigger one, always contain the small one, with the numbers n smaller. Here we have how it's work. We have one expansivity, it's equal to, it's equivalent to expansive. Have n expansive here, have n plus 1 expansive. Then we have the countable expansive that and measure that is equivalent to measure expansive. And then we have the continuized expansive and the entropy expansive defined by Bowen. So in 2016, we gave the example that these guys are not trivial. They are not just the expansive, and then we have the other one cannot be any expansive at all. We have examples here that are not trivial. And these examples that we show are, they don't have they are not tame. They have infinite many chain recurrent classes. So it's also, and here we have also more that there are other examples for this guy, for countable. And we have this entropy expansive, that the definition from Bowen, that there is delta dot such that this Bowen ball has topological entropy 0 for each point in X. And then finally, we have the last definition that is continuized expansive, that there is delta such that for each, here we cannot use the Bowen ball, but for each non-trivial set that is a continuum, meaning that it's compact and connected, then we have sub-iterated in Z, such that this diameter of some iterated is greater than delta. For this continuized expansive homomorphism, we have these really interesting theorem that when we have CW expansivity, we have the topological dimension of the set finite. So to the continuized expansive, we cannot make like a theory of expansivity for high dimension, for infinite dimension. So this is one question that I have been thinking recently, that I will skip this thing, just talk about this. The time is short. I will talk about this work in progress, that expansivity theory in infinite dimension, that it's related with this CW expansivity definition, that we have this theorem that the topological dimension must be finite. And we have this nice definition of entropy expansive. What we thought, it's just, there is a notion, it's called mean dimension, and there is also the topological mean dimension. And the topological mean dimension has the nice property that when the entropy, topological entropy is not infinite, so the mean dimension is always zero. So my guess is put here, instead of topological entropy, to put here the topological mean dimension or the mean dimension. And then search for examples that possibly can have, can have an infinite dimension. This is what I am working now, and I think it's just 1 minute, and I will just stop now. So dziękuję i instalar Felix.
All right, are there any questions?
So when you were talking about the types of expansivity, you said there is an equivalence between measure expansivity and countable expansivity.
Yeah.
Could you explain in a few words how it happens? Because it looks to me like we could have a counter set with zero measure.
This was proved by I don't know the proof, to be honest. It was proved by Archie and Servant, I guess. It's a Chilean guy, and the other one is from Venezuela, but now he works in Chile. But I don't know the proof, to be honest. It was not really directly. The proof was not directly. It was take some time.
Okay, thank you.
Right, any other questions?
So in this this map you had of the different kinds of expansivity, like n implies n+1 and all, are there other implications that you think are probably true, but that you haven't been able to prove, or is that map pretty much the state of things?
What
Like
this
the previous slide, that one.
This
Yeah.
one?
Are there other things, other types of implications that you hope to prove?
No, we have examples that show that these implications are proper. This thing we have example here that's not here that's not here. An example here that's not here. We have all these implications are not trivial.
Okay, thank you.
Any other questions? All right, if not, let us thank the speaker again.